Hey everyone, ever wonder how Netflix can pick your next favorite show in a split second? That's dynamic programming at work. In this course, we'll break big, hairy problems into bite-sized pieces, remember each answer, and stitch them together into super efficient solutions. Think of it like prepping ingredients for a stew. Chop once, reuse often, and have a delicious meal in no time. By the end, you'll master optimization tricks for everything, from pathfinding to resource planning. Ready to supercharge your problem-solving toolkit? Let's dive in. Building on what we've just seen, dynamic programming is a method for solving problems that exhibit two key properties. First, optimal substructure. The best solution to the overall problem can be built from the best solutions to its smaller subproblems, and these relationships are captured by a recurrence. Second, overlapping subproblems. When the same subproblems keep popping up during recursion, we solve each one just once and reuse its result, saving expensive computation. Together, these features let dynamic programming turn exponential time recursive algorithms into efficient, polynomial time solutions. To see that in action, let's examine the classic, naive Fibonacci function. It starts, if n is 0 or 1, return n. Otherwise, return fib n1 plus fib n2. Below, the recursion tree for fib 100 splits into two branches at every call. You'll notice fib 98 and fib 97 popping up in both branches, and then again and again, so we end up recomputing the same values over and over. Since each level roughly doubles the number of calls, this naive approach runs in O2 to the power of n time, which quickly becomes impractical as n grows. Now that we've seen how naive recursion explodes exponentially, let's turn our attention to pattern matching, measuring similarity or finding the optimal alignment between sequences. Three classic examples are the longest common subsequence, edit distance, and general alignment problems. You encounter these every day. Typing suggestions that correct or complete your words, intrusion detection systems, hunting suspicious patterns in network traffic, and antivirus scanners checking files against known malware signatures. On the left, a document review tool highlights matching text and reports a similarity index to flag potential overlaps. On the right, an antivirus scanner compares file contents against its virus definitions, showing how many objects it scanned and whether any threats were found. Both interfaces demonstrate how core pattern matching algorithms power real-world software. Now let's dive into another example of the longest common subsequence problem. We have two strings, algorithm and alignment. Although their letters aren't all in a row, one common subsequence you can extract is ALGM. In the diagram, the first string appears on top and the second along the bottom. Straight vertical and diagonal lines mark matching letters. A lines up with A, L with L, then G in algorithm aligns diagonally with G in alignment, and finally M at the end. Those four letters, ALGM, form one valid LCS. Building on our example, let's simplify our task. Rather than hunting for the entire common subsequence right away, we'll first compute its length, denoted LCSAB, and postpone reconstructing the actual sequence until later via backtracking. The big question is, how do we define the right subproblems to compute LCS efficiently? Take algorithm and alignment again. You'll recall their longest common subsequence has length 4 thanks to those matching letters. Next, we'll dive into breaking this length computation into smaller, more manageable subproblems. Building on that idea, let's look at what happens when the last characters of A and B match. If two strings share an LCS of length L and A equals B, that matching character must sit at the very end of the subsequence. In other words, LCS AB equals L implies the LCS of A1 M1 and BN1 has length exactly L1. If it were any smaller, you couldn't reach L by adding the final match. If it were any larger, you'd exceed L. For example, take A equals algorithm and B equals alignment, both end in M. The LCS of algorithm and alignment has length L1. And appending that last M brings us exactly to length L. Continuing from our previous discussion, let's look at the optimal substructure property when the last characters of A and B don't match. Suppose A and B have lengths m and n, and their LCS has length L. If A does not equal B, that final mismatch means the LCS must come from dropping one of those last characters. In other words, the length of LCS AB equals the larger of 1. LCS of A, 1 with B, N1, or 2. LCS of A, 1 M1 with B. In the diagram, algorithm ends in M, while alignment ends in T. Since ma does not equal t, we either ignore the T and find the LCS of algorithm versus alignment, or ignore the M and find the LCS of algorithm versus alignment. This branching into two smaller subproblems is exactly what lets us build the full solution with dynamic programming. Building on the last slide, here we see the optimal substructure property at work for the longest common subsequence problem. Let A and B have lengths m and n, and let their LCS be length L. If A and B don't match, the LCS can't include both of those characters. Instead, it must come from one of two smaller subproblems. Either drop the last character of B and compute LCS A1, B1, n-1, or drop the last character of A and compute LCS A1m-1, B1. In either case, one of these subproblems still has length L. On the right, you see A equals algorithm ending in M and B equals alignment ending in T. Since MUD does not equal T, the common subsequence of length L must result from removing one of those final letters and solving that smaller problem. This branching gives us the exact recursive relation for LCS whenever the last characters differ. Building on that, let's recall the classic LCS recurrence. To compute Ci, j, if x and y match, we take Ci-1, j-1 plus 1. Otherwise, we pick the larger of Ci, j-1 and Ci-1j. Now, picture calculating Cxn10. Because x does not equal y, we're forced to compute both Cx9 and C910. Each of those calls, in turn, splits again whenever the characters don't match. If you trace the recursion tree down just a few levels, you'll spot the same subproblems, like C9, 9, or C8, 9, being recomputed in different branches. This explosive branching with overlapping calls is exactly why a naive recursive approach to LCS is so inefficient, and why we switch to memoization or a bottom-up table to avoid redundant work. Building on that insight, we now turn to a top-down dynamic programming approach with memoization for computing sequence similarities. First, we allocate an m times n table C and initialize every entry to null. Then, whenever we request TC by, we check. If it's still null, we compute it. If x and y match, we set C by jg equals C-1, j-1 plus 1. Otherwise, we take the maximum of C by j-1 and C-1 and C-1, j. Once computed, each value is stored in C so that any future call for C simply returns the memoized result, avoiding redundant work. In the first grid, you see our empty table at the outset. In the second grid, we zoom in on filling the bottom right cell C. The two blue neighbors show the subproblems being compared, and the red cell marks the new value we record. Picking up where we left off, this slide walks us through the top-down, memoized dynamic programming approach for finding C-men, the length of the longest common subsequence. First, we examine the recursive pseudocode. Whenever we invoke compute, ij, we check whether Cij has already been filled. If it's still null, we compute it as follows. If x equals y, set C, j1 set, equals C-1, j1 self, plus 1. Otherwise, set C equals max, C-1, C-1, hack still. Once we've recorded that value, we return it. And thanks to memoization, each ij pair is actually computed only once. Below the code, 2 meters times n grids illustrate this process. On the left, the table is empty. On the right, a few cells are shaded to show partial evaluation, with the most recent entry highlighted in red. In the worst case, we'll fill every cell exactly one time, and so the overall running time is proportional to the number of distinct subproblems, m times n. That gives us a theta mn time complexity for computing C with memoization. Now that we've seen the top-down memoized approach, let's flip things around and explore a bottom-up strategy for the longest common subsequence. Instead of making costly recursive calls, we build a two-dimensional table C that stores every subproblem's result. We begin by laying out a grid whose first row and first column compare against an empty prefix, so we initialize all those entries to 0. With those boundary values in place, we then proceed row by row. At each cell, if the characters match, we set Ci son to the diagonal value +1. Otherwise, we take the maximum of the cell above or to the left. By reusing these earlier results, we avoid recursion entirely and compute the final answer in theta mn time. Building on our bottom-up strategy, let's set up our first LCS example. We have two strings, x equals abcb, length 4, and y equals bdcab, length 5. To compute their longest common subsequence, we allocate a two-dimensional table C with 5 rows and 4 columns. Across the top, indices j equals 0 through 5 are labeled with y's characters. Down the side, I equals 0 through 4 are labeled with x's characters. Right now the table is empty. Row 0 and column 0 serve as our base cases, all initialized to 0. Next, we'll fill each cell based on whether the characters match, or by taking the maximum of its neighboring entries, building up the LCS length one step at a time. Continuing from our setup, we're now computing the LCS between ABCB down the side and BDCAB across the top. Our table has dimensions m+1 by n+1, and we begin by initializing every cell in row 0 and column 0 to 0. After all, matching any sequence against an empty one yields a length of 0. If you look at the code snippet, you'll see that for I equals 1 to m, we set Ci 0 equals 0. And for j equals 1 to n, we set C0, j equals 0. With these boundary conditions in place, we're ready to fill each inner cell by checking for character matches and taking the maximum of the neighboring values. Now that we've set our boundary conditions, let's begin filling the DP table for x equals ABCB down the side and y equals BDCAB across the top. At cell I equals 1, j equals 1, we compare x equals a with y equals b. They don't match, so we follow the else case of our recurrence and take the larger of the cell above or to the left. Since both C, 0, 1 and Con 0 are 0, we set Con 1 equals 0. You can see the arrows pointing up and left, showing where that maximum comes from. With this first non-trivial entry complete, we simply continue across the row and then down the table in the same way. Let's move on and see how matches start to influence our values. Building on our earlier work, this slide shows the dynamic programming table we'll use to find the longest common subsequence of x equals ABCB down the side and y equals BDCAB across the top. We start by initializing every cell in row 0 and column 0 to 0, since an empty prefix has no common subsequence. From there, each entry Ci is filled in row major order according to the recurrence. If Xi equals Yj, set Ci equals Ci Bti1, J1 plus 1. Otherwise, set Ci equals max. Ci1, J, Bearsul. With these base cases and rules in place, the table gradually fills until we reach C4, 5. That final value gives us the length of the LCS and guides the reconstruction of the actual subsequence. Next, we'll see how each cell value is determined step by step. Now we're filling the entry for I equals 1 and j equals 4, comparing the first character of xa with the fourth character of y, also a. Since they match, we apply the match rule. Con 4 equals C03 plus 1. The diagonal value C03 is 0, so we write a 1 in cell, 1, 4. You'll notice the two matching A's are circled in the sequences, and an arrow points to our new entry. From here on, every other cell will use the no-match rule, taking the larger of the cell above or to the left until the table is fully populated. Next, we'll see how this plays out across the rest of the grid. Building on our last example, we now fill the cell at row 1, column 5 of the DP table for x equals ABCB and y equals BDCAB. Here the highlighted characters are x equals A and y equals B. Since A does not equal B, we follow the else case of our recurrence. We take the maximum of the cell above, C0, 5 equals 0, and the cell to the left, C-own, 4 equals 1. That gives us C-own, 5 equals 1, effectively carrying forward the best subsequence length found so far. This perfectly matches the formula below. If the characters don't match, C equals max, Ci1, Cj1. Continuing from our last example, let's now fill in cell 2, 5 to compute the LCS length between x equals ABCB down the side and y equals BDCAB across the top. As before, our table C mile at AI Carlisle's Jejos is initialized with zeros along row 0 and column 0. At I equals 2 and j equals 5, we see x equals b and y equals b, circled in red. Because they match, we use the match case of the recurrence. C2, 5 equals C-own, 4 plus 1 equals 1 plus 1 equals 2. That result goes into the highlighted cell, and an arrow points back to C-own 4 to show the diagonal dependency. Of course, whenever characters differ, we'd fall back to taking the maximum of the cell above or to the left. Building on that, let's now find the longest common subsequence between the string. X equals ABCB, down the left, and y equals BDCAB across the top. In our grid, each entry CI records the length of the LCS for the first I characters of X and the first J characters of Y. We start by initializing row 0 and column 0 to 0. Then, for every cell, we apply two simple rules, ni. If X equals Y, we set CI J characters of Y, ni characters of 1, ni J1 plus 1, ni. Otherwise, we take the maximum of the cell above, Ci1, and the cell to the left, Cij1. As you fill in the table, you'll see it bump up whenever there's a match. A at 1, 4, B at 2, 1, C at 3, 3, and finally B at 4, 5. At that last cell, both characters are B, so we grab the diagonal value C, 3, 4 equals 2, add 1, and record 3. That bottom right entry tells us the LCS length for the full strings is 3. Building on that example, here's the pseudocode for computing the longest common subsequence of two sequences x and y. First, we set m and n to the lengths of x and y. Then we initialize the first row and column of our table C to 0. This handles any case where one sequence is empty. Next, for each I from 1 to m and each j from 1 to n, we compare x to y. If they match, we assign Ci jj equals Ci1 j1 plus 1. Otherwise, we take the larger of the two neighboring entries, equals max Ci1 j Ci1. After filling in every cell, we return the completed table C, and its entry at m pom n gives us the length of the longest common subsequence. Now, let's see how the pseudocode unfolds in a dynamic programming table. This slide displays the table for finding the longest common subsequence between our two strings. The rows track the characters of X, A, B, C, B. The columns track Y, B, D, C, A, B, and we've initialized zeros along the top row and leftmost column to handle the base cases. Whenever X matches Y, we grab the value from the cell diagonally above and to the left, and add 1. If they don't match, we carry forward the larger of the values from above or from the left. You'll notice the circled cells marking the three key matches that incremented our count, B at 2, 1, C at 3, 3, and B at 4, 5. Finally, the red arrows trace the backtracking path from the bottom right corner back to the start, picking up those letters in reverse. Reading them in forward order gives us the LCS BCB. Building on that chart, the classical dynamic programming algorithm for LCS actually fills an entire n by n table, so it costs on squared time and on squared space. In our example, we've laid out xi equals abcb along the rows and yj equals bdcab across the columns. We start with zeros in the top row and left column, then for each cell we add 1 when the characters match, or otherwise take the maximum of the cell above or to the left. By the time we reach the highlighted bottom right cell, we see the LCS length is 3. It's an elegant, straightforward method, but storing every cell forces that quadratic overhead. So the natural question is, can we do better, either by cutting memory down to linear or by speeding up the computation? Indeed, we only need linear space during the actual DP fill. The kicker is that building a full m times n table can swallow up memory when sequences grow large. Instead of storing every row, we keep just 2, the current one and its immediate predecessor. In our example, the top row, I equals 0, is initialized to zeros, shown by the red line. Then, when we compute the next row for character A, we reference only that 0 row, which produces match scores of 1 at columns 4 and 5. By continually overwriting the oldest row, we slash our space requirement from OM down to ON without changing the final alignment. Building on that trick of reusing only 2 rows at a time, Hirschberg's algorithm pushes linear space alignment even further. Suppose we need FMN, the optimal score for 2 sequences of lengths m and n, but we can't afford the full m times n table. Here's how we do it. First, split the longer sequence of length m right down the middle, m/2 on the left, m/2 on the right. We run a forward DP over the left half and record f of m/2k for every prefix length k of the second sequence. Next, we reverse both the right half of the first sequence and the entire second sequence. Then run another DP to get frm/2 nk for each suffix of the original second sequence. Now we have 2 score curves as functions of k, one from the forward pass, one from the reverse pass. We simply add them pointwise and pick the k that maximizes f of m/2k plus frm/2 nk. That k is exactly where the optimal alignment splits the second sequence. With that split in hand, we recurse independently on each half, always using only linear memory for each DP pass. It's this clever divide and conquer step that drives Hirschberg's space complexity down to OM plus n, without sacrificing optimality. Building on that divide and conquer insight, let's see how we collapse the full m times n matrix down to linear space. First, we split the grid right down the middle at column m/2. On the left half, we run a forward DP to compute fm/2 k for every row k. On the right half, we run a reverse DP to compute frm/2 nk. Adding those 2 score arrays produces a single peak at row k tems, and that point must lie on the true optimal path. In the diagram, the split column is shaded orange and the chosen row segment is highlighted. Once we've located this midpoint, we simply recurse on the 2 smaller submatrices on either side, reconstructing the full alignment while only ever storing 1 column of scores at a time. Building on our midpoint trick, here's how we perform the full alignment in linear space by recursively splitting the DP matrix. First, we take the entire m times n grid and cut it down the middle along the columns. Each half is m/2 columns wide. At this dividing line, we compute the best row index k stewed man. That's exactly where the optimal path crosses. Next, we treat the upper left block of size m/2 times k times and the lower right block of size m/2 times nk asterisk as 2 independent subproblems. For each block, we again split at its column midpoint. Find the new crossing row and recurse. In the diagram, green and blue regions mark the active submatrices, red lines show the current splits, and arrows pinpoint where the alignment path crosses each line. By alternating left and right in this way, we only ever store 1 column of scores at a time, yet we still recover the exact optimal alignment in linear space. Now, building on our previous discussion, we split the original problem domain into 2 exactly equal-sized subproblems. Look at the shaded orange areas, the top left block and the bottom right block, each covering half of the input space. The dashed vertical lines mark the midpoints where we divide the domain, and the smooth black curve running from the upper left corner down to the lower right corner represents the boundary we're tracking. By isolating the curve's behavior within those two orange regions, we reduce our size n problem into two independent tasks of size n/2 each. We can solve each shaded subproblem on its own, then combine their solutions to assemble the full answer. This gives us a clean divide-and-conquer approach that mirrors exactly how we split and conquer our alignment matrix, except now we're doing it directly on the problem domain. Building on that idea, this large rectangle represents our original problem. We've carved it into 4 equal shaded blocks, each exactly 1/4 the size of the whole. The overlaid curve traces how a single computational task threads sequentially through all 4 regions, capturing the essence of a divide-and-conquer step. Here, we reduce a size n problem into 4 independent size-n/4 subproblems, then combine their results to reconstruct the final solution. Building on our divide-and-conquer framework, let's summarize the algorithm's resource usage. Its space complexity is OM plus n, meaning we only need linear extra memory in the sizes of our 2 inputs. On the time side, each phase does OMN work, and when you multiply that by the series 1 plus 1/2 plus 1/4 plus, which converges to 2, the overall running time stays at OMN. In short, we get linear space and a runtime proportional to m times n. Pretty efficient. Building on our linear space, OMN time foundation, let's now see how to speed up the dynamic programming routine by tapping into parallel hardware. First up, can we compute whole rows or columns of the score matrix in parallel? 2 clear paths emerge: multi-threading with threads or OpenMP, and vector programming via SIMD instructions. In the top right diagrams, you'll notice the contrast between a scalar operation, which handles one AB pair at a time to produce C, and SIMD operation, which packs multiple A values into a single vector register and churns out several C results in one instruction. Below that, you see our DP matrix SHI labels down the side, A, B, C, B, and YJ, labels across the top, B, D, C, A, B. The first row and column are initialized to 0. A circled A on the row and a circled B on the column mark the cell we're about to compute, and arrows from its left and top neighbors highlight the data dependencies that constrain how much of the matrix we can parallelize. By laying out both threading and SIMD opportunities alongside these dependency arrows, we can craft a computation schedule that maximizes hardware utilization without ever breaking correctness. Building on our exploration of threading and SIMD, this slide shows how we can fill a 2-dimensional dynamic programming table in parallel by sweeping along its anti-diagonals. Since each cell depends only on its top left and top left neighbors, once all cells on earlier diagonals are complete, every cell on the current diagonal becomes ready for computation at the same time. In the example, you see a diagonal wavefront moving down and to the right, with 4 cells highlighted in unison, each one now independent of its peers on that diagonal. By processing these anti-diagonals in parallel, we can dramatically slash overall computation time compared to a strictly row-by-row or column-by-column approach. So far, we've seen how parallel anti-diagonal sweeps speed up DP. Next up, the 4 Russians method, which pushes us into subquadratic time by trading a bit of extra memory for lightning-fast updates. Here's how it works. First, pick a small block size and exhaustively precompute every possible DP outcome on a block of that size. Then, at runtime, slice your full n times NDP matrix into those same blocks. Instead of filling each cell one by one, you simply look up the precomputed result for each block's input frontier. In the illustration, you can see the DP grid overlaid with thick block boundaries. The red line marks the main diagonal frontier, while the green zigzag traces an example alignment path. By filling each block in constant time via cache lookups, we reduce the overall complexity below the usual quadratic bound. Building on that, we pick a small block size T and exhaustively precompute every possible pairwise alignment of T-length nucleotide strings. Because there are 4 bases, this gives us a 4-T times 4-T table of mini alignments. When we align 2 full sequences of length n, we simply split each into n^T blocks and look up the result for each block pair. That way, the total work scales with n rather than n^T squared, delivering a huge speedup by trading costly dynamic programming updates for lightning-fast table lookups. Building on that idea, let's define T as our block size, and n as the full sequence length. Instead of filling an n by n dynamic programming grid entry by entry, we partition it into T by T blocks. For every possible pair of T-length nucleotide strings, there are 4-T choices each. We precompute their optimal alignment and store it in a lookup table of size 4-T by 4-T. This one-time pre-computation costs on the order of 4-2T squared time. When aligning 2 full sequences, we simply step through the n2 by n possible grid of blocks. Each block's optimal values come straight from our table in constant time, so the overall dp runs in ONT_NTT equals ON squared / T. In this graphic, the large alignment matrix is tiled into blocks, with the red optimal path jumping from one block to the next, each block solved instantly via lookup. The key question we're left with is, how do we choose T to balance the upfront cost of precomputation against the speedup we gain in the main DP? To answer that balancing act, we introduce the 4 Russian speedup for our dynamic programming problem. Here's the idea. We break the n times NDP grid into smaller t times t blocks, picking t equals log n/4. Because our alphabet has size 4, each block's boundary conditions can take on 4 different patterns, and stitching 2 such blocks together still covers all n entries in a row or column. Before we dive into the main DP, we spend O4-2T L-T squared time precomputing every possible block result. Since 4-2T equals n, that upfront cost is ON log squared n. Then, in the DP itself, we fill each t times t block by a constant timetable lookup, which drives the total running time down to ON squared / log n. On the slide, the left shows our big DP matrix tiled into t times t blocks, with the red trace marching block by block and arrows pointing to the tiny precomputed tables. On the right, you see the master lookup table, indexed by all 4 possible row and column boundary patterns. This simple block lookup strategy shaves off a logarithmic factor in runtime. Pretty neat, isn't it? Now let's walk through a concrete example with 2 sequences, x equals ABCB and y equals BDCAB, by building the classic dynamic programming table. We begin by inserting a 0 row and column for our base cases. Then, for each cell C, we follow a simple rule. If x matches y, we take the diagonal value and add 1. Otherwise, we choose the larger of the cell above or to the left. Notice that once the table is fully populated, the bottom right entry is 3. So the longest common subsequence of x and y has length 3. With that 2-sequence result in hand, we're ready to extend this same principle into 3 dimensions to include sequence z equals ABCA and compute the 3 LNCS. To illustrate that jump from 2D to 3D, on the left is a 2-dimensional grid made up of evenly spaced horizontal and vertical lines. A bold path runs from the top left corner to the bottom right, showing how points connect when you only move along the x and y axes. On the right, you'll see a 3-dimensional wireframe cube. In addition to the x and y directions, depth along the z-axis comes into play, and the cube's interior is subdivided into smaller cubes. This side-by-side comparison highlights how adding that 3rd dimension transforms flat shapes into volumes and dramatically ramps up the complexity of modeling and computation. Now that we've seen how adding a 3rd axis transforms flat grids into cubes, let's tackle the longest common subsequence across 3 strings. Suppose our sequences are x equals ABCB, Nunmher, y equals BDCAB, Nunmher Allings, and z equals ABCA, Nunmher Damher. We build a three-dimensional table L where each index tracks our position in one string. Whenever x, y is equals AB Canmher, and z equals AB CB AB, listens 1 ZL, AB AB equals 1, plus L, listens once 1 1 cool, listens 1 mile 1 Menui Canmher, listens 1 mile 1 Bort, extending our subsequence by that common character. If they don't all match, we consider dropping one character at a time, looking at L1, L1, and L1, and take the maximum. By filling out this I times j times k grid, we eventually compute the length of the longest common subsequence in. More generally, for n sequences each of length k, you end up filling an n-dimensional array of size k caret n, so both time and space grow on the order of k caret n. Building on that three-string example, let's generalize to k sequences. If we tackle KLCS with straightforward dynamic programming, we end up managing a k-dimensional table, and the running time explodes exponentially in k. For instance, suppose our sequences are .x equals ABCB, .x equals BDCAB, .x equals ABCA, all the way up to x equals ABAAAB. At each DP update, you must consider every possible index combination across those k strings. In other words, the total number of states, and thus the time required, grows on the order of n, making an exact KLCS solution infeasible as k increases. Transitioning from KLCS's computational hurdles, we're now asking two key questions. First, can we leverage word embeddings, think word2vec, to spot and even correct misspellings instead of relying on simple lookup tables? And second, how do these vector-based methods compare to classic string algorithms like dynamic programming LCS or edit distance in terms of accuracy, speed, and ease of implementation? Let's turn our attention to the classic knapsack problem. Imagine you have a set of items, each with its own weight and value, and a knapsack that can carry at most W units of weight. Your mission? Pick a subset of those items so that the total weight stays within that W limit, while the total value is as high as possible. For instance, suppose you have 3 items. Item 1 weighs 1 unit and is worth 8. Item 2 weighs 3 units and is worth 6. Item 3 weighs 5 units and is worth 5. Which combination of these items gives you the greatest value without exceeding your weight capacity? Building on that example, here we illustrate the knapsack problem with 7 everyday items, each defined by its weight and value. Here's a quick rundown. 1. Teacher's wallet. Weight, 20. Value, 39. 2. Little B figurine. Weight, 6. Value, 12. 3. Algorithm textbook. Weight, 24. Value, 55. 4. Mobile phone. Weight, 7. Value, 15. 5. Chalk. Weight, 8. Value, 20. 6. Laptop. Weight, 22. Value, 44. 7. Report card. Weight, 4. Value, 11. Our task is to select a combination of these items that maximizes total value without exceeding the knapsack's weight capacity. Notice how the textbook and laptop offer high value but also carry substantial weight, whereas smaller objects like the report card or B figurine keep weight low but contribute less value. Striking the right balance among these trade-offs is at the heart of the knapsack problem. Building on our everyday example, let's now formalize the 0 to 1 knapsack problem. Imagine you have a knapsack that can carry up to W units of weight and a collection of N items. Each item I has an integer weight W and an integer benefit B. Your task? Decide, for each item, whether to include it or leave it behind, so that the total weight never exceeds W, and the combined benefit is as large as possible. What's the best way to pack your bag for maximum gain? Let's find out. Now let's visualize the 0 to 1 knapsack problem in picture form. On the left, you see a knapsack with a maximum weight capacity of 20. On the right are 5 items, each shown as a colored block alongside its weight and benefit. For example, the first item weighs 2 and offers a benefit of 3. The second weighs 3 for a benefit of 4. The third weighs 4 for 5. The fourth weighs 5 for 8. And the fifth weighs 9 for 10. Because each item can either be taken or left out, there are 2 caret-n possible ways to pack the knapsack. The task, then, is to choose a combination of these items whose total weight doesn't exceed 20 while maximizing the sum of their benefits. Building on that illustration, we now introduce a second parameter, W, to capture the knapsack's capacity. With this new dimension, we define B as the maximum benefit achievable by selecting from the first K items without exceeding capacity W. For example, B520 asks, what's the best picks from items 1 through 5 that fit in a knapsack of size 20? To compute it, we compare 2 choices for the 5th item, include it or leave it out, and pick whichever yields the higher total benefit. On the right, you can see our 5 items listed with their weights and benefits. Item 1 weighs 2 and gives a benefit of 3. Item 2 weighs 3 for 4. Item 3 weighs 4 for 5. Item 4 weighs 5 for 8. And item 5 weighs 9 for 10. This formulation lets us build the optimal solution step by step. Building on that, we can express BW with a simple recursive rule as the maximum value you can pack from the first K items into capacity W. There are 2 cases to consider. 1. If the weight of item KW exceeds W, it can't fit, so we just inherit the best solution for K1 items at capacity W, namely B1, sit or nod. 2. Otherwise, we compare 2 options. Dot A. Skip item K and stick with B1, W, or dot B. Include item K, which gives us its benefit B, plus the best we can do with the remaining capacity, BK1, W, W. We then choose whichever option yields the higher total. In other words, the optimal subset of the first K items at weight W either excludes item K or includes it and adds its benefit to the best solution for the leftover capacity. Now, building on our previous discussion, let's take a closer look at the core recurrence that fills our knapsack table B. For each item K and capacity W, B is defined by 2 cases. First, if item K's weight W is greater than W, we simply can't include it, so B equals B1W. Otherwise, we compare 2 options. We either leave item K out, yielding BK1W, or we include it, which gives us BK1WWW plus its benefit B. Whichever choice produces, the higher total becomes B. In other words, the best subset of the first K items at capacity W is either the optimal subset of the first K1 items at W, or that same subset at W-W with item K added, whichever delivers the greater benefit. Now that we've nailed down the classic knapsack recurrence, let's see it in action. Recall that B is the best benefit you can get from the first K items with capacity W. If item K's weight is more than W, you simply can't take it, and so B equals B1. Otherwise, you compare 2 options, skip it or include it, giving dot B equals max B1, B1, B1 plus B. On the left, you'll see what happens if we try to compute B520 by pure recursion. It splits into B420 and B4 10 plus 9. Then each of those branches again and again, resulting in tons of repeated calls. On the right is our DP table setup. The total capacity W is 20, and we have 5 items with weights, 2, 3, 4, 5, 9, and benefits, 3, 4, 5, 8, 10. By filling in a DP table instead of recomputing subproblems, we guarantee that each K-W pair is solved just once. Since K runs from 0 to 5 and W from 0 to 20, that's 6 times 21 equals 126 distinct subproblems in all. Now that we've seen how dynamic programming tables eliminate redundant work, let's walk through a small 0 to 1 knapsack example with 4 items and a capacity of 5. Our items have weight value pairs of 2, 3, 3, 4, 4, 5, and 5, 6. We'll build a table with capacities 0 through 5 as rows and items 0 through 4 as columns, where column 0 and row 0 are all zeros, because with 0 capacity, or 0 items, the maximum value is 0. From here, we fill each remaining cell one at a time. If the current item's weight doesn't exceed the row's capacity, we compare two choices: the value of excluding the item, the cell immediately to the left, versus including it, the value from the same row minus the item's weight in the previous column, plus the item's value. Whichever is larger goes into the current cell. By the time we reach the bottom right corner, we'll have the optimal total value for all 4 items at capacity 5. Now that we've set up our problem, let's dive into the table. On the left is our DP matrix, rows indexed by item I and columns by capacity W. And on the right, we list each item's weight and benefit. 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6. We begin by filling row 0 with zeros, since with no items the total value is always 0. Next, at I equals 1, our first item, weight 2, benefit 3. Any capacity W below 2 can't accommodate this item. Those cells stay at 0, as indicated by the arrow at W equals 1. Once W reaches 2 and above, we make a choice for each cell, skip the item and carry over the value from the row above, or take the item and add its benefit to the best value at capacity W2. Comparing these two options is exactly what drives the rest of our table fill. Continuing our knapsack walkthrough, we still have 4 items, and capacity W equals 5. Recall each item's weight benefit. Item 1, 2, 3. Item 2, 3, 4. Item 3, 4, 5. Item 4, 5, 6. We'll build the table B for I equals 0, 4 and W equals 0, 5. As before, row 0 and column 0 are all zeros. No items or no capacity means 0 benefit. Now let's process item 1. W equals 2, B equals 3. For each capacity, W. If W less than 2, we can't include it. So B, W equals B, 0 equals 0. Once W is greater than or equal to 2, we compare two choices. Exclude item 1, B0, that's 0. Man these extern, man 1. Include item 1, B plus B0. W2 equals 3 plus 0 equals 3. Since 3 greater than 0, we set B, B2, Mandia 1 equals 3. That means for W equals 2, 3, 4, 5. B Mandia 1, all equal 3. Mandia 1, all equal 3. Underneath the table, you'll see the core recurrence. If W is less than or equal to W, then if B plus B I1, W dash greater than B I1 W. W B equals B plus BI1 W dash greater dot else dot. B equals BI1 W dot else dot. BI equals BI1 W dot L. We've just applied that rule for I equals 1. Next, we'll move on to item 2 and fill row 2 in exactly the same way. As we just saw, we've initialized our DP table and applied the recurrence for item 1. Here's a quick recap of how we fill row 1 for our knapsack of capacity 5 with 4 items. Capacity 0 and 1. Item 1. Weight 2, benefit 3 doesn't fit, so the cells remain 0. Capacity 2, including item 1, yields 3, which beats excluding it, 0, so we set B, own 2, equals 3. Capacity 3, excluding leaves us with B0, 3 equals 0. Including gives 3 plus B0, 1 equals 3, so we record 3 again. Capacities 4 and 5. The same logic applies, since B0, 2, is still 0, including item 1 continues to give a benefit of 3. Notice the arrow at capacity 3 Because W is less than or equal to 3, we compute dot B plus B0, 3 to 2 equals 3 plus B0, 1 equals 3. And since that exceeds B0, 3, we choose to include item 1. Below the table, you see the general recurrence. If Wi is less than or equal to W, then B equals max gable below plus B1, general 1, lidi W.wi, gan I dotty equals B1, zy equals B1, li dotty. By working row by row like this, we'll build up the optimal solution for the full knapsack. Next, we'll move on to item 2 and fill row 2 in exactly the same way. Building on that, we're now solving a 0 to 1 knapsack with 4 items in capacity 5. Our items are 1. Weight 2, benefit 3, 2. Weight 3, benefit 4, 3. Weight 4, benefit 5, 4. Weight 5, benefit 6. We build a table B, where I runs from 0 to 4, and W from 0 to 5. Row I equals 0 is all zeros. No items yield 0 benefit. In row 1, item 1, W equals 2, B equals 3. We set B own 2 equals 3. And for any capacity 3, 4, or 5, we also record 3, since that's the best we can do so far. Moving to I equals 2, item 2, W equals 3, B equals 4. Let's zoom in on column W equals 1. The item's weight exceeds this capacity, so it can't fit. We simply copy the previous row's value. B2, 1 equals B, 1 equals 0. In general, for each cell B, we first check if the current item fits. If it does, we compare 2 options. Include it, benefit underscore I plus B, A1, W weight underscore I, dot. Exclude it, B, 1, W, and take the larger. If it doesn't fit, we just carry forward, B, 1, W. Repeating this process for all items and capacities fills the table and yields the optimal knapsack benefit. Building on our previous table, we're still tackling the 0 to 1 knapsack with N equals 4 items and capacity W equals 5. Each item I has weight W and benefit B as follows. 1. W equals 2, B equals 3. 2. W equals 3, B equals 4. 3. W equals 4, B equals 5. 4. W equals 5, B equals 6. We build a table B where I runs from 0 to 4, the number of items considered, and W runs from 0 to 5, the current capacity. The recurrence looks like this. If W is less than or equal to W and B plus B, 1, W dash greater than BI1, dot B equals B plus BI1, W dash dot else, B equals BI1, W dot ETB. Let's walk through one cell. I equals 2. Item 2 has weight W equals 3, benefit B equals 4, and capacity W equals 2. Since W3 exceeds the available capacity, 2, we can't include item 2. We fall into the else clause and simply copy the value from the previous row. B2, 2 equals B own, 2 equals 3. Remember, B own, 2 was 3. The best we could do with only item 1. This shows how the table carries forward the best value when the current item won't fit. Continuing our DP table for item 2 at capacity 3. Since item 2 weighs exactly 3, we have 2 options, include it or skip it. If we include it, we take its benefit of 4 and add it to the best value for the remaining capacity of 0. That's 0 plus 4 equals 4. If we exclude it, we simply carry over the previous best at capacity 3, which is 3. Because 4 beats 3, we record 4 in row 2, column 3. This really captures the heart of our bottom-up approach. At each cell, we compare include versus exclude and pick the higher benefit. Next, we'll move on to filling the cell for capacity 4. Building on our last step, we're filling a bottom-up DP table B for a knapsack of capacity 5 with 4 items. 2, 3, 3, 4, 4, 5, and 5, 6. Rows correspond to capacities 0 through 5, columns to items 0 through 4, and all base entries start at 0. Now, at I equals 2, the second item with weight 3 and benefit 4, and W equals 5, we compare two choices. Excluding item 2 leaves us with B own 5 equals 3. Including item 2 consumes weight 3, so we add its benefit 4 to B von 5 to 3 equals B, 2 equals 3, giving us 4 plus 3 equals 7. Since 7 greater than 3, we record B2 5 equals 7. This mirrors our recurrence. If W is less than or equal to W, then B equals max. B1. B plus B goal amine W exactasu dot else dot equals B goal amine sactasu. In this case, including item 2 yields the optimal value of 7 for capacity 5. Continuing our example, let's build the bottom-up DP table for the 0 to 1 knapsack problem with 4 items in capacity 5. Our items are 1. Weight 2, value 3. 2. Weight 3, value 4. 3. Weight 4, value 5. 4. Weight 5, value 6. We'll fill a table B where I ranges from 0 to 4, items considered, and W from 0 to 5, capacity. Every entry in row 0 or column 0 is initialized to 0. Now let's zoom in on cell B, 3, 4, which considers the third item, weight 4, value 5, at capacity W equals 4. According to our recurrence, if W underscore I is less than or equal to W dot, BI equals max. BI1 W B underscore I plus BI1 W dash W underscore I dot else here W underscore I equals 4 and B underscore I equals 5. Excluding item 3 leaves us with B2 4 equals 4. Including it gives 5 plus B2, 0 equals 5. Since 5 greater than 4, we set B3, 4 equals 5, as highlighted by the arrow. By repeating this inclusion versus exclusion check for every I and W, we eventually fill the entire table and uncover the optimal knapsack value. Now that we've seen how to fill a single entry, let's build out the full 0 to 1 knapsack table for our 4 items and capacity 5. Remember, our items are 1. Weight 2, benefit 3. 2. Weight 3, benefit 4. 3. Weight 4, benefit 5. 4. Weight 5, benefit 6. We'll create a table with rows for capacities 0 through 5 and columns for items 0 through 4, initializing the top row and left column to 0. For each cell B, we ask, does item I fit? WI is less than or equal to W. If so, we compare the value of including it by plus B1 WWI to the value of excluding it B1 W. Whichever is larger becomes B. Otherwise, we simply carry over B1 W. For example, at item 3, weight 4, benefit 5, with capacity 5, including it, gives us 5 plus B2, 1 equals 5 plus 2 equals 7, which is better than excluding it, so we record 7 in that cell. Once we've processed all 4 items up to capacity 5, the bottom right entry shows 7, the maximum benefit we can achieve. Building on our previous example, let's talk about runtime. The classic 0 to 1 knapsack algorithm runs in ONW time, where W is the capacity. If W itself is enormous, say 10 to the power of 15, then the running time becomes completely impractical. In fact, in the worst case, W can grow as 2 caret n, so even dynamic programming ends up taking exponential time. The table on this slide drives the point home. It lists 6 items, with weights ranging from tiny values all the way up to trillions. You'll even spot a single textbook weighing 2.4 times 10 to the 12 units. Once numbers get that big, filling every entry from weight 0 to W simply isn't feasible. Building on that observation, the classic 0 to 1 knapsack problem still only admits a dynamic programming solution running in ONW time, where n is the number of items, and W the capacity limit. Because W itself can blow up exponentially in the input size, this approach is deemed pseudo-polynomial rather than truly polynomial. In other words, despite the DP's apparent efficiency, its worst-case runtime remains exponential. Ultimately, knapsack stays an NP-hard challenge,